Hello everyone, this is a presentation of our joint paper with Michael Benedikt on how to generate collection transformations from proofs, preferably in an efficient manner. To start off, let us take a look at the high-level problem of producing programming artifacts from logical specifications. In most cases, when designing a program of any sort, the programmer will have some idea of how it should behave before writing any line of code. Such specifications can often be written as formulas describing an input-output relationship. Programming is difficult, so one worthy goal of formal methods is to provide tools to help produce programs that match specification, or even to have tools produce those programs automatically without the intervention of the programmer. Not all formulas make sense as specification. In the interest of sanity checking and reducing the problem space, you can ask them to be well behaved in some ways. One such requirement, totality, is that there always exists an output related to the input. Another, functionality, is that the relation defines unambiguously at most one output value per input value. In a purely functional setting, both of these requirements together would completely determine the semantics of the desired program f. With this in mind, it is natural to consider variants of the general algorithmic problems of synthesis, where, in addition to having a specification as input, we are also provided a certificate, that is, a proof, that the specification is reasonable. Those certificates can help in computing the desired implementation f. Otherwise, the problem of synthesizing from specifications alone is often intractable. One way of leveraging proofs is via the Courier-Watt correspondence. Typically, one can read off, in linear time, a functional program f from a constructive proof of totality of phi, and this f will produce an output satisfying the specification phi. Note in particular that we require phi to be total, but not necessarily functional. In this talk, we'll be interested in the opposite scenario. We say that phi is an implicit definition if it defines a partial function. The goal then is to find an algorithm taking as input a proof of functionality of some phi's and outputting f's compatible with the input relations. In a nutshell, our paper is concerned with this later scenario where programs are taken among a class of tractable transformations between nested sets. These nested transformations are meant to operate on particular databases where relations can range not only on tuples of atomic data, but also on sets and relations. I will first spend some time giving a layman explanation of the nested relational model and how to specify transformations. I will also define the target language for extraction, which is going to be the nested relational calculus, which I'm going to call NRC for short. Then, I will present an efficient extraction procedure which computes NRC terms from constructive functionality proofs. Finally, I will present a more general result stating that explicit definitions may in principle be extracted from non-constructive functionality proofs. This goes through a non-constructive model theoretic result about multi-sorted theories and interpretations. So, let's start with introducing the setting of nested sets. Throughout the talk, we will work with the following type system containing an anonymous space type U of O elements and typeformers for sets and products. Once a semantic interpretation for U is fixed, each type has an obvious set theoretic semantics, as in the displayed examples. This model generalizes the relational model used in database theory by allowing arbitrary nesting of the set typeformer. What we call a nested transformation is then nothing more than a function with a fixed input and output types, taking nested sets to nested sets. Here are the two running examples I will use throughout the talk. The first one does not involve nesting. It takes a set A to its preimage via an input relation. The second one takes a flat relation to the collection of pairs associating every element of its codomain to its preimage by R. Given that we are working with sets, it is then natural to use the language of set theory with an equality and membership predicate to write specifications. We will, however, work in a multi-sorted setting where variables in formulas are explicitly typed according to the type system I have just discussed. Accordingly, we will have one distinct membership and equality predicates at each type, and we will also allow terms for tupling and projections to handle Cartesian products. Rather than general first-order formulas, we will focus on formulas where all quantifications are bounded by some term. This fragment is already quite expressive, and it is sufficient to give full specification of our two running examples. You can now read one such specification for the preimage function, which states that every element of the input should be related to an element in the input set, and that every pair of the relation intersecting the input set should populate the output accordingly. Similarly, the transformation collecting all preimage of singletons can be described by a conjunction stating that there should be one suitable pair in the output per element of the codomain of the input relation, and that every pair in the output actually corresponds to a preimage. Now that we have our logical framework, we should turn to our explicit language for transformation of nested sets. Our language of choice is the nested relational calculus, which is standard for manipulating nested relations because of its simplicity and its practicality. Its terms denote transformations taking as input multiple nested sets, described by variables collected in context gamma in the present slide, to a single nested set. Its core syntactic features handle tuples, projections, and two set formers, the singleton construction and the big union. Note that the latter is the only operator in this grammar that bind variables. For functional programmers, you can regard the singleton and union as the return and bind operation associated with an underlying power monad. In addition to these core constructions, NRC also features syntax for finitary unions and set difference. While not officially part of NRC, it was also convenient for us to introduce an additional operator, picking elements from singleton sets to deal with some corner cases. This does not ruin the good properties of NRC and only serve to deal with those aforementioned edge cases, so I will sweep that under the rug for the rest of this talk. NRC is powerful enough to encode our running examples. While I will not orally detail the formal expressions that you see here, it can be noticed that they use syntactic sugar that I did not give in the previous slide. Among these derived constructions, note the encoding of booleans in the type system using the unit and the set type formers. The syntax of NRC is then rich enough to encode basic predicates such as equality and set membership, as well as case analysis. In fact, we can go further and note that every delta zero formula can actually be translated to a Boolean NRC query and vice versa. Using this embedding and case analysis, it means that we can filter sets by means of delta zero separation. This points to a tight link between delta zero specifications and NRC, although it only pertains to transformations outputting booleans for now. We will thus now consider delta zero formulas as specifications for general nested set transformations. So recall that we are interested in implicit definitions, that is, specifications together with the proofs of functionality. For now, we will consider a subclass of implicit definitions that are intuitionistic. What we mean by that is that the accompanying proof of functionality should be constructive. That is, it can use a non-constructive principle such as exclude middle. For such definitions, we can show that not only we may extract compatible NRC terms, but we can do so efficiently if we are provided a normalized constructive proof of functionality. This extends a previously known procedure for transformations between flat relations to the nested setting. Before going into the details of the proof, let us detail some potential scenarios where this sort of procedures might be helpful. A first generic use case concerns injective or invertible transformations. Suppose that we are given an NRC term that we suspect is injective, such as our running example collecting all fibrous fibs. Then we may easily turn such a term into an implicit definition. Indeed, a proof of injectivity is nothing more than a proof of functionality for the reciprocal relation. We can then use our procedure to extract an NRC term, inverting our original transformation from this proof of injectivity. A second generic use case is the caching of intermediate computations. The basic idea is that in a sequential program manipulating nested sets via NRC expressions, one could look for functional dependencies between variable assignments to avoid spurious computations. While these prospects are enticing, one caveat is that we should always be able to produce the required proof of functionality to make these methods work. This may be challenging to do, either by hand or automatically. Furthermore, our procedure only works with a certain intuitionistic sequence calculus rather than standard calculi implemented by off-the-shelf theorem provers. Before even describing our constraint proof system, let's first argue that we can restrict our attention to certain delta zero formulas, which are given by the following syntax without primitive negations and only an equality predicate for all elements. The basic idea is that the membership and equality predicates are definable inductively over the types by using a standard encoding trick. Similarly, since we allow primitive disequality for all elements, negation is definable by induction over the syntax. This in particular means that all those derived equalities are de facto extensional without having to assume additional axioms. In fact, we will assume no further set theoretic axioms. Then, for functionality proofs, we will use, without loss of generality, a sequence calculus with a judgment between a list of atomic memberships, a list of delta zero formulas, so those two lists forming the hypothesis of the sequence, and a single conclusion, as is customary in intrinsic logic, with the additional twist that this conclusion will be either a membership, an equality, or an inclusion between sets. The intuitionistic sequence calculus then contains rules tailored to this setting, where the right-hand side of the sequence have those specific shapes, and every quantifications are bounded. So as to make our work easier in the sequel, we make certain non-standard constraints on the rules. For instance, we only allow left rules to be applied if the conclusion of the sequence is a membership predicate. Using standard proof theoretic techniques, we can however check that the usual intrinsic sequence calculus LJ does not produce more proofs. Furthermore, this correspondence is actually efficient. Translation of cut-free proofs in LJ to this system can be achieved in polynomial time. In this restricted system, we can thus model proofs of functionality as follows. Proofs are then, as usual, formal proof trees as pictured here. We now want an extraction procedure that reads off an NRC term from such derivation. Note that those derivations do not necessarily look like functionality proofs at every step. Therefore, we need to come up with a more general inductive invariant to maintain, which is not so clear at first glance. To come up with this invariant, we took inspiration from Craig interpolation, a celebrated result in logic. It states that any implication between two formulas phi and psi, whose sets of relation symbols and constants are not necessarily the same, may be factored as two implications, phi implies theta and theta implies psi, where the middle formula theta, called the interpolant, only features constant and relation symbols which are common to both phi and psi. This is a robust result that holds true in many settings. Of interest to us is that if phi and psi are delta zero, then we can check that the interpolant theta is also delta zero. It is also an effective result as the interpolant may be computed in linear time from cut-free derivations. In fact, this can be used right off the box to produce an extraction procedure for transformations between flat relations. For the nesting setting, we need to go a bit further. Now, suppose that we have a proof that two formulas gamma and delta prove some formula psi relating two elements L and R, L being a free variable in gamma and R a free variable of delta. Then, we may always compute an NRC expression E that only depends on variables which are common to both gamma and delta that relate to L and R in a meaningful way. If psi is an equality or an inclusion, E is sandwiched between the sets L and R. If psi states that all L is a member of R, then E should be a bound for L. The statement is reminiscent of Craig's interpolation, but it is somewhat stronger. In particular, it functions as a backbone for extraction procedure, which just consists in applying this to the specific case where gamma and delta are two copies of the specification that we want, and the conclusion is an equality. We can check that in this case, the proof artifact is just a functionality proof. As announced earlier, this procedure and the proof work via a straightforward induction over proof trees. Of note is that we do use interpolation as well as the findability of delta zero separation in certain crucial steps. All in all, this results in an efficient procedure which can extract E by iterating a single time over the whole proof tree of an intrinsic proof. Now, with the time left, I would like to discuss the generalization of this result to classical proofs. One first easy remark is that although intrinsic implicit definitions cover a lot of interesting cases, there are implicit definitions which are definitely not intrinsic. Nevertheless, we also showed that the correspondence with NRC extends to classical implicit definition. Our proof uses a bit of model theory and is not constructive. In particular, we do not know if there is an efficient procedure to synthesize NRC terms from classical proofs, even classical cut-free proofs. There are two steps. First, we use the fact that transformations definable by NRC are those defined by logical interpretations. Then we use a more general result about implicit definability in multi-sorted structures and interpretations to conclude. The basic idea we use to employ model theoretic arguments is that a nested collection X may be regarded as a multi-sorted structure whose signature depends on its type and whose elements should generate every subobject of the collection X. Once this is done, we may consider a natural notion of maps between structures, which is the notion of interpretations. Without going into details, interpretations are essentially a principled way of describing maps by way of first-order formulas. In particular, products, definable subset, and quotient of structures are definable by interpretations, and interpretations are also closed under composition. The crux of the matter is that, under the aforementioned encoding of nested objects as structures, NRC and interpretation coincide. With this result in hand, we may think about more general results about implicit definability in model theory. Given a two-sorted theory, we say that a sort tau implicitly defines a sort sigma if and only if partial isomorphisms only defined on the sort tau always lift uniquely to an isomorphism over both tau and sigma. To make our overall argument, we make a reduction turning an implicit definition of nested transformation to a multi-sorted theory where we think of tau as the input sort and sigma as the output sort. Then we use a general theorem turning implicit model theoretic definitions to interpretations, and those interpretations may be translated back to NRC, giving us our overall result. This therefore leaves open the problem of efficiently generating transformations from classical proofs. To do so, one may attempt to constructivize the general multi-sorted theorem we just discussed, and see if we may get an algorithm with a reasonable complexity. Another way of attacking the problem would be to try to generalize the higher type interpolation lemma I discussed earlier to classical sequent calculus, that is, a sequent calculus that will allow multiple conclusions. So far, both options seem challenging to us. We think that dealing with the classical case is not only an interesting theoretical problem, but that it could also be helpful in practice. Like, one could hope to tweak the procedure to extract programs from proof certificates produced by general-purpose automatic theorem provers. There are naturally further topics to be considered. We are currently formalizing our extraction procedure in Coq, with the hope of obtaining a certified runnable artifact to extract NRC terms. Another thing to look at would be to flesh out the courier word correspondence for NRC, noting that similar work was already undertaken for a non-typed version of NRC by Vladimir Sazonov. Finally, we also hope to find other application of implicit definitions other than nested sets. Thank you for watching all the way through, and we will be happy to take questions at the Q&A session at the conference.